my I would like first to thank Victor. I just met him a 2 month, maybe 1 month ago that I was visiting, and I was visiting his institute, and we had a chance to talk a bit, and I gave a talk and a course, and Hugo was there, so I'm very honored to have had Hugo as my student, which is also a great researcher at this institute. He is a student of Gustavo, which is also a friend of Juantil. And Victor, you are very welcome. Thank you very much for this. And, please tell us a little bit about you, maybe your institution, and you are welcome. Thanks a lot.
Thank you for having me, Alvaro. It was a great pleasure to meet you. Well, let me talk about my institute a little bit first. I'm at the University of São Paulo in the Institute of Applied Mathematics and Computation. Specifically, we have a center that has computation and mathematics applied to the industry. So this talk is going to be about a project we had with a ride-hailing service that hired us to perform some exploration on their data. It was a very short project we had, but in this center we are able to experiment with a lot of different companies. Especially Luis Gustavo Nonato, that is the main leader in the group, also friends with Alvaro. He works a lot with crime data. So this is sort of a crime data project too. So my career so far, I've studied at the ICMC, not with Luis Gustavo, but with André de Carvalho. André de Carvalho is very focused on machine learning in general. So I learned a lot while being there. I had the opportunity to work with Natalie Jakovic at the American University. I had the opportunity to work with other really great professionals. And then now I'm working with Luis Gustavo at this group with computation applied to the industry. There was a very odd introduction. I didn't prepare myself to introduce myself. Sorry.
No problem. That's great. Perfect. Thanks a lot. By the way, I'm sorry I don't know many of your co-authors, but Thales Vieira, is he a sociologist?
No. He also works with Luis Gustavo Nonato in this project, but he is from another university.
Okay.
But it's also computer science.
Okay, great.
The new, you're talking about sociology because Luis Gustavo Nonato has a new project on crimes with a really important center in sociology focused on crime analysis. So this project will take place in the near future. We have a meeting next month. So it's going to be multidisciplinary with people from sociology and computer science to work on crime together. That's going to be really good, but it was not what happened at this particular project.
Okay.
So these are the co-authors of the work. Carilla, two Thales, Victor, that's me, and Luis Gustavo Nonato. The other line of this presentation is talk about a little bit of ride-hailing services for those who are not familiar with. What are the risks for the drivers on this kind of services? The company that we were working together, they were really interested on having some insights about these risk factors. So they wanted to know more about the data, like a visualization tool. So this is more of what we're going to talk about in this presentation. During the project, there was only a 6-month long project. It was very short. It was a very short project. So there was a lot more that we could have done with that. But I think I'm very proud of what we achieved on a really short amount of time. So we implemented a library for urban data integration that we call City Hub. And we also implemented a visualization tool called Ordena that helps the specialists on the ride-hailing services to explore those kind of data. And after we're going to conclude and with some future works too, that we could have done more in this aspect. Okay. So for those who are not familiar with ride-hailing services, are services, transportation services on demand. You call it and you have it. They are usually performed through a mobile application. So the passengers, they request rides, and the drivers usually use their own personal vehicles to provide the transportation to those passengers. And the passengers, they are matched with the nearest available driver. That's what the app, the mobile app do. And the fare is calculated based on the distance and time traveled. So the passengers pay the fare. The fare is what pays the driver and company and ride-hailing company both. This is what usually happens. So the drivers are really on their own. And it happens a lot. They suffer from verbal aggression, physical aggression, assault, kidnapping, and can end up even in murder. Just a data from here that we had in 2021, from January to June in 2021, at least 43 ride-hailing drivers were killed while working, while driving in Brazil. This is murder is like the lower rate of thing to happen. So the others happen really in a greater amount than that. So it's very it's a very warning to have their own. So the company was interested on giving some help through data. So the data we had was a case study in São Paulo city. So a ride-hailing company provided the data. They provided a fraction of the rides from January to September in 2021. That fraction of data corresponds to almost 90,000 records. So just a fraction of the, we don't know how much they have because it's kind of safety for confidentiality. They don't talk, they don't express the real numbers. We had just a fraction of the rides. And they given information for each trip were the origin and destination coordinates when the passenger called in the app, the period of the day that they called, the number of rides both passenger and drivers had in the platform, payment method, and for trips with occurrence, the type of the occurrence. It can be robbery, physical aggression, kidnapping, physical injury, and other. Especially for this project, we decided to keep with robbery and kidnapping because we understand that it has a different concept from physical aggression and physical injury and insults. Because robbery and kidnapping, they are usually, most of the time, they're planned, while physical aggression and insults, they're not. Most of the time they're not planned, they happen, maybe some people are more prone to, they tend to make physical aggression and to cause physical aggression and to insult people more. But it's different from robbery and kidnapping that usually they're planned. When they call the service, they know that this is what they will try to do. So we focused on both robbery and kidnapping. That may end up in murder or not. The data is really balanced when we consider this type of occurrence. So we have a fraction of 1 to 87 between rides with occurrence and regular rides. And we have a greater interest in identifying rides with occurrence. So there is clearly a difference in interest in the classes. What I mean with that is that misclassifying a ride with occurrence has a different cost of misclassifying a regular ride. So some insights about what were asked for and how this project to explain how this project turned out this way and not other way. So the company was really interested in identifying the risk factors in different regions. And they were more interested in exploring and having insights on the problem rather than an automated model to label the rides. So they were not really into an automated model to implement in the app so we can help the driver to, that was our first thought. Let's build a model that will help them if they can implement it in the app. When the driver is to accept a ride, it can warn it, like it may be this ride may be prone to happen this or that, like a layer of security in the app. But there are several things to tackle to achieve this, and in a short period of time, it would not be easy. Like we would have to deal with fairness and not an injustice with poor regions, and it's really hard to tackle those things in a very time constraint like we had. So in this regard, we came up with a visualization tool so they can understand the factors better, and they can explore this data, and they can come up with some policies inside the company to help the drivers throughout their work. So we focused on building a visualization tool for data exploration. Still, we built a machine learning model, and we incorporated it into the visualization tool. So this is what was brought to us, and we ended up with. This was the track we trailed. So we wanted to incorporate external and open available data to reach the information they had. They had information about the passengers, the origin and destination, and payment method, and etc. And we knew that this wouldn't be enough to understand the problem. So we incorporated some socioeconomic data that were gathered from the Brazilian census database. I don't know about you guys, but here the last census was collected in 2010. That's a very long time ago. So it's outdated, but still that's what we have. We incorporated some subnormal agglomerates information that it's the regions where the urbanization growth was uncontrolled. some favelas lay in the subnormal agglomerates. So we're here tackling a lot of delicate information to put in a model and trust it a long way, not to be fair. So we had to have a lot of I don't know. We had there's a very sensitive topic. We also incorporated street crime data like robbery, mobile theft in the streets, and etc. I saw someone raising their hands.
Yes, there is a chat question actually. Minoru ask, risk factor means risky request for drivers?
Yes, well, so the dynamics are a little bit like that. The passenger asks for a ride, and the driver can accept it or not. What are the risks of accepting this ride right away with the information you have right away? What are the informations you have right away? You have the origin and the destination desired by the passenger. You have their experience in the platform. You have the payment method, and you have all the other informations around this origin and destination they asked. So what can be, so the risk for the driver is to be assaulted or kidnapped. So what are the factors that make these risks higher in this situation? These are the factor risks they were interested in finding out. Is it clear? Thank you. We also wanted to incorporate some public transportation facilities. It's near metro, it's near a bus station. This can help a lot in identifying that in streets information. It's really worth incorporating, because they told us that they usually ask for a ride that may end up in some dead end street, that it's not, that there are no really light streets, or it's not vigilant enough, so they can commit their crimes. We also wanted to incorporate some hotspots information, and etc. So all these different types of data, they come from different sources and different formats. And for example, the ride-hailing data is a tabular format, and we had a pair of coordinates, right? The origin and the destination of the ride. The street crime data in the public transportation facilities, they are points in space, they're coordinates, but the census, they are polygons in space, and they aggregate several data. The subnormal agglomerates, they are also polygons, they are like regions in space, but with only a specific characteristic. The dead end streets are actually information retrieved from the city graph, the street graph from the city. So this information, they come from a very broad source of data and format of data. So we came up with a library for urban data integration that we called City Hub. So in order to implement the visualization tool, we needed to combine all this different information. So we came up with this library to integrate all these sources. It's available on GitHub for anyone who wants to explore it. But what it does basically is you have a area of interest, a city of interest, for example. In this case of studies, the city of São Paulo is a São Paulo city. It's easy to download the street graph of the city, where all the streets are connected, and you have this in a graph form. And what we do with this library is that we create layers upon this city street graph, layers of different types of information, as many as you want. So understood that we needed this in order to achieve a visualization tool. So this is a first step to achieve that. Since our research group works a lot with crime data and this type of urban data, it came really handy to have a library like that, not only for this project, but for all the other projects in the research group that may need it. So we made it as general as possible, so anyone with some specific project on urban data can use it. In order to discretization and also they didn't want to give us the right coordinates of this, because you can reconstruct it, and this is a safe problem with protected data. So we projected all the coordinates to the closest corner, street corner that was available. So the library also does that. If you give a coordinate, it projects to the closest corner in order to discretize. So we end up, instead of having lots of coordinates, they're all discretized to the closest corner in the city graph, the street graph of the city. You may interrupt me at any time if you want. If you have any doubt, please don't let it pass. Just interrupt me. Raise your hands like Daniel did. It was great. So one layer that we were interested in is the point-based layer, like public transportation. So you can put it as a layer in the city graph, and the library is implemented to take statistics about it. Like, I have a coordinate of interest. What are the points that have a radius of 200 meters, for example? So you can retrieve this information to build features, for example. We can also implement regional layers that, for example, here are subnormal agglomerates. They look like, I know that they look like dots, they look like points here, but if you notice, they're not. For example, this one is a very large region here. They're all regions, but most of them are really small regions. So you have this layer of regions that it only gives you one type of information, like it belongs to it or it doesn't belong to it, or it's close to a region like that, or it's not close to a region like that. It's different from a polygon aggregate layers, like a census data that you have several information about that polygon, like average income, unemployment, literate children, the distribution of the residents' ages. So you can also build this layer upon the city street graph. You can also build a sparse layer. This is useful, for example, in weather treatment, because, for example, in São Paulo, you have these 3 main weather stations, and it's difficult to get what is the rainfall for a specific coordinate in the city. What we usually do is we interpolate the information from these central stations to have information about that area specific. Of course, there are lots of error involved to it. It's the best that we can do. And you can use your own function to interpolate this information in the library. Also, the dead-end streets and the near dead-end streets were retrieved from the city street graph. So here are examples of dead-end streets. Those red dots, those blue dots are near those dead-end streets, because sometimes you don't need to fall to a dead-end street specifically. Just being near there is enough to commit some crime, for example. So with this tool, we can build several layers on top of that city graph, and we can retrieve information from all these layers. This is an example. Actually, this code that we're going to show you, it's outdated. It's not exactly like that it works right now, but it works as an example. So you can import the city street graph. You can load a polygon mesh. You can add some features to this polygon mesh. You can save after you added all the layers you wanted. You can save it as an object, and you can use it after, for example, to retrieve a specific feature of a coordinate, or to retrieve all the features that all layers had given to that point. So it was very handy for us to build this, because we were interested in building a visualization tool about all the data we could gather on the rides, and also to build a predictive model. So after we had this library, and after we could build a database with all the information we gathered, we were able to build a predictive model and a visualization tool. So let's talk about the predictive model first. So to apply the machine learning techniques, we built a data set, which each instance is a ride. Remember that the rides are a combination of two coordinate points, origin and destination in the city. And so each instance is a ride, and each feature are the information about the ride that we already had, like the number of rides in the platform, paying method, and etc. And we also combine this information as features, all the external variables for both origin and destination, using our library in City Hub. The classes are binary. We focused on irregular rides and rides with occurrence, remembering that the rides with occurrence here are the robbery and kidnapping one, with a balanced ratio of 1:87 between the two classes. To build the predictive model, we did a hyperparameter tuning. So we tested two different pre-processing steps, combined or not, a feature selection step and a random undersampling step to tackle the imbalance. Also, among the hyperparameters we tested in the classic machine learning algorithms, we tested the decision tree, random forest, SVM, logistic regression, neural network, and XGBoost. Most of them, they have also a parameter to tackle imbalance, that is class weight. We also included that in the hyperparameter tuning. So we ended up with 2,868 model candidates. And how we evaluated them. Since the data may change through time, we cannot guarantee, cannot take all the rides into account randomly. We split it into time. So we consider the data from February to April to train, to induce all the candidate models. And then we tested them on the data from May to July. We used the G-mean metric to pick the best model out of all of them. Why the G-mean metric? Because when we have imbalance, if we use a metric like accuracy, I don't know how much you're familiar with some data imbalance problem. But if you use some accuracy method, like I'm gonna take all the correct rights that I classified over all the rights that I could have classified, it gives you a number. And once we have a lot of regular rights and just a few rights with occurrence, if we get all the regular rights right and all the rights with occurrence wrong, we're still gonna have a really good value for the metric. That's what we want. We use the G mean because it's a geometric mean between the rights you got right for occurrence and the rights you got right for the regular ones. So this weights the same way both classes. Okay, someone raised their hand.
There's a question. Daniel has a question.
Yes,
Yes.
it's an easy one. I'm guessing why do you guys use undersampling instead of oversampling?
We used undersampling instead of oversampling because there's a very few. It's 1 to 87. If we consider oversampling, like to reach something interesting, like really a volume of data, we would have done a lot of oversampling. Just for you to notice, in between August and September here, we have almost 18,000 regular rights and just 162 rights with occurrence. If we have to oversampling it by mode or random oversampling or ADASIM or anything like that, we would have needed a lot of oversampling that can characterize the data a lot.
Okay, okay, thank you.
And also, when you apply mode, they're probably very sparse data, and you may end up with something that was not really real for this type of problem. I don't have anything against oversampling. I don't have anything against mode. I already used it, but it's important to understand your data, understand your application, and see if it fits or not for that. And we thought that it didn't. We may be wrong, but we were cautious about it. Just that.
Well, thank you very much.
Thank you. So we picked the best candidate using the data from May to July, and those hyperparameters, those preprocessing techniques, we applied in all the data from February to July, and we tested it just to validate from August to September. And these are the results from August to September. The best model candidate was an XG boost combined with random undersampling and no feature selection. That XGBoost already does the feature selection. And the G mean we achieved was 88%, with a positive recall of 87% and a negative recall of 90%. So if we look here at this confusion matrix, like I said before, we had almost 18,000 regular rights and about 162 rights with occurrence. We were able to get 87% of all the rights with occurrence correctly, and we were able to get 90% of the regular rights correctly. That's great. But if we noticed, the precision here is very low. This usually happens when we have imbalanced data, because we have some different interest in the different classes. We cannot miss there is a difference of cost of misclassifying a class with occurrence, a right with occurrence, that is higher than misclassifying a class, a regular right. So if we consider that we are only getting like 10% of the data wrong here for a regular class, so we can achieve an 87% of positive recall. So this is a trade-off. When we talk about imbalanced data, we are usually talking about a trade-off between how much we want to get from the minority class and how much we want to get from the majority class, how much you want this threshold to be. And this looked nice for us and the company, but they were satisfied with this number, with this precision here. I think I talked all I wanted about it. Okay. Any doubts to here?
Do you guys created any custom metrics such as an F beta or something like that?
No, we didn't change the beta parameter for the F measure nor any of that, because they were already satisfied with that, and this was not even their. They were not really interested in applying the model itself. So we were happy with the Genie, and we stick to it.
Okay, thank you.
But we could have tested a lot of different measures, like the F measure you told, with changing the beta parameter, the Genie. There are several. There's the area under the precision recall curve. There are several measures we could have used here. Okay.
No, I wonder if, are you going to talk about the risk identification factors?
Just a little bit. We use this model because it's very domain specific. It's different from one region to another. But we build up a visualization tool so they can explore the data in this regard. So we're going to talk about some of the factors, but I'm not really going to get really into what are the factors, because they're testing the visualization tool too. So they need the experts need to actually evaluate it. That's how they wanted it to happen.
Great.
So the visualization tool, the requirements they have, that they want to have insights about the data. They wanted to better understand the rights that have the same art. So they have some really things in their mind right away. They knew that there are people that commit some crimes that they have some pattern. They knew that some of them always called a ride from a specific region or origin region or destination region, and there was a pattern in this that they always committed this crime, and they wanted to visualize it better. They also wanted to better explore how are the characteristics of the short distance and long distance rides. So in order to achieve that, we needed to consider the city itself. It's a very large city with 1,521 square kilometers with a population of 12 million people. It's a lot of people. So in order to fulfill those requirements, we understood that we needed to sort all the corners in São Paulo city, so we can have corners close to each other, close in one-dimension space. So we can build a scatter plot between origin and destination for visualization purposes. So we have coordinates. There are 2 dimensions, and we want it to be like 1 dimension. Some things crossed our minds, like when we were exploring it, like TS and E, to reduce it to 1 space. It didn't work out very well as we wanted, but Donato came up with the idea of applying a fiddler vector to it. So the fiddler vector is used a lot in the graphs theory. It takes into account the connectivity of the graph, how the nodes are connected in the graph. You use a Laplacian matrix, so we can take the connectivity into account. Taking the returning of the fiddler vector applied to it, we can imagine that we can have this scatter plot with origin and destination, which here we have all the possible corners of origin, and here we have all the possible corner destinations, in street corner destinations in the city. And if you pick up a dot here, it would represent a right, which this is the origin and this is the destination. But here the origin and the destination is represented in one dimension rather than in two dimensions. Is it clear so far? Okay.
Clear, yeah.
So if you pick this right specifically here, you can see that it has this origin here and this destination here in the city. So this right has these coordinates here.
I just have a question. Sorry, Victor. Is there a way of making this mapping such that something which is close in the left-hand graphic is somehow close in terms of the map on the right?
Like this, if you're asking if this region here.
Yeah, just take one point which is close to the point you already have there, and then if you have a point close to that one here, is it close in some sense on the right?
Yes. Yes. So I got your. So what we were aiming for, it was exactly that. So if you consider this scatter plot here, and if you consider that the diagonal, the main diagonal here, we wanted this, the points laying in the diagonal to be short distance strips, because they come from places and goes to nearby places. So they come from origins and goes to nearby origins. Does that make sense?
Yeah, I'm just curious, how can you make that work if, I mean, it's like in non-linear order, it's like a part, I don't know, it sounds.
Yeah. That was the idea. That was Luis Gustavo Donato's idea with the fiddler vector. We're gonna show how this worked in parts, because we have this problem. It has two dimensions, and if you project it into one dimension, you lose some information.
Right.
But the projection was quite interesting. It was quite interesting. So this was what we were aiming for. So things in the diagonal here are short distance strips, because the origin and the destination are nearby corners. And the idea was to have also here, like if you select some rights that have nearby origins but spread destinations, this would work. And if you wanted some nearby destination with spread origins, you needed to select some points like these ones. And these ones, they are actually long distance strips because they have origin that are not close to the destination. Does that make sense?
Yeah, I'm quite impressed. Are you going to show us the formula, or what, this particular peddler?
It is a, I can show you, I can open another slide. I did not get into the Fiedler vector specifically. We had a lot of, we had other co-authors. This was not, it was something that I did, but not really into it. But I can discuss it a little bit. I can. Luis Gustavo Donato is the one, the best one to discuss this, actually. But I can open the Laplacian matrix. It's actually the second eigen value of the Laplacian matrix, and you have this for you build the matrix with the connected dots. We have a matrix with all the possible corners, origin, and destination. And you have the connection between them in the graph. So if they're connected in the graph, you have a number indicating it. And you also have a extra column that connects all the corners with all the other corners, but with a very, very low number. When you do that and you take the Laplacian matrix and you do this, and you get the second eigen value of that Laplacian matrix for each corner, you end up with a value that you can sort, that you can order. Does that make a little bit of sense?
Yes, no, that makes a lot of sense. So it's quite interesting. I didn't know. Very interesting. Yes. Okay.
Okay. If you're happy with the explanation.
No. I mean, the second eigenvector, I didn't know it had this sort of the Laplacian. This sort of
because the first one of the Laplacian is zero. Is always zero. So you need to get the second one, because the second one is going to show you some connectivity of the graph.
Okay.
So we were hoping something like that, and these are true pictures of the rides here. So when we're talking about short distance trips, we're talking about something like this, but there is a limitation. When we order all the possible coordinates and projected in one single dimension, like this colored gradient here, we end up with something like this. This is what is happening with Fiedler. So the lower numbers here, they come here and go to the greater here. They are really distant. This red is really distant to this blue thing. But we end up with something like really stretched. I don't know. It's not really how we're supposed to want, because if we get a point here and a point here, they may have the same distance of a point here and a point here, but the Fiedler will show you that this is further away than this one, and it's not. I don't know if it's making sense for you guys what I'm talking about right now, but the ordering is not really as smooth as we wanted. This thing here that crosses between blue and orange, there's actually a river here. So as we use the graph, it's usually in the connectivity of the nodes, but this river, of course, has many bridges between these 2 points. So it's not really, they're not really that unconnected. They're all also connected, but because of this this physical barrier, which has some bridges on it, it affected the whole Fiedler index. Does that make sense to now? So we have, it works better than the other techniques we tested, like TS&E, but it still has its limitations. Maybe all techniques will have, it's hard to project the two dimensions into one and not lost, and to not lose some information. So taking these limitations into account, we implemented the visualization tool, which we have the origin and destination here with the fiddler vector, with the fiddler index here. We have some green dots that represents regular rides and some yellow dots that represents rides with appearance. And once you select a region there, it opens up the map so you can see what are these origins and what are these destinations. And you can also bring some information about the feature importance for the model to predict this ride specifically. So we have the model that we ended up with, that was the XGBoost. We applied the Shapley technique to get the most important values, the features, for those specific rides that were selected on this scatter plot here. So in this case, the most important feature to classify those rides were the number of rides the passenger had in the platform, the payment type, and we also had some other information like some favela, near favela, and other features. Also, so this is what this feature importance field does. We also,
Victor, sorry to interrupt you, but what is the SHAP values for the in criminal incidents, or the the unsafe incidents?
So the Shapley values for those. Let me take some steps behind. The Shapley values is a technique to understand what any classification, what are the important features for any classification model. So it's a technique that it basically tries out different values for each feature and see how those different values turns into different outcomes. So it tests the model with different, in a very brief way, it takes out the model with different values, and it checks out how those different values affect the outcome of the model. If you change a value of a feature and it dramatically changed the outcome of the model, it's probably an important feature for the model to get that outcome. So, for example, here, for this specific rides, the most important features were, the most important feature was one feature that they already had given us. That is the number of rides that the passenger had in the platform. Is it clear? Was that your question, Alvaro?
No, I sort of understand SHAP values, but I understand it's a local measure. So I could actually evaluate the SHAP values at some particular rides, as you are doing here, I believe. But if I would like to know for the rides that ended up in an unsafe trip, which are the SHAP values of those particular trips?
That was a safe trip. What are the Shapley values for those that were classified as safe?
Unsafe.
Unsafe. It's possible to do this. It's usually, in general, it would be the number of the experience of the passenger in the platform. and the payment method are usually on the top, because passengers with lower experience in the platform, they usually create an account just to make that crime. So they have something close to zero experience, close to zero rights in the platform. So they just create that so they can commit the crime. Also the payment, because they usually ask cash payment instead of credit card, because with the credit card, you would have your information in the platform, and that is not safe for them. So these are the characteristics they already knew when they were working with us. They already knew that this pattern happened. What happened here is that the model showed it, that those are really usually the most important characteristics to take into account, but they are also interested in other characteristics they can explore, because sometimes people with known rights in the platform and they want to pay in cash, they may want to ask for a ride, or sometimes taking just one into account, it's not only enough, and so they wanted to explore it better, the data. That's why they asked us in the visualization tool. So yeah, does it answer better your
yes,
your question?
Yeah.
So with this visualization tool, we can also understand how well the model went on this specific rights. So yellow means rights with occurrence, and green means rights, regular rights. We can see here that you did really well on both of them, but with a little bit less on the regular rights, because you have this, it's really small here, should have zoomed it or something. But you can see that you committed some errors here. And by clicking on each one of these characteristics, you can also you can also check the characteristics of those rights selected before. So for example, here, those regular rights that are there, most of them were paid in cash, but it's a different distribution of the rights with occurrence. So just considering cash payment would not be enough, because you would be classifying all these regular rights as rights with occurrence. You have to take into account a lot of the other characteristics, but it's not enough, because a lot of regular rights also pay in cash. So with this visualization tool, you can actually explore all of the other features here, and sometimes they are more important to the occurrence, to the rights with occurrence with compared to the regular rights. For example, here there's information about hotspots in the region, and so you have really to deal with it. For example, if it's afternoon, it's probably more prone to help classifying better the regular rights. So the visualization tool is basically this, but involves a lot of background techniques here, like Fiddler vector to sort all the pointers, build an adequate model to understand the characteristics of the rights you select, knowledge of the problem and the city to understand the specific regions you were working with. You can also select from the map and get the information you need. You don't need to select on the scatter plot. So it's a really interesting visualization tool for this specific problem. Here are just some examples that you can select rights, select some rights. Then you can understand the feature importance of the rights that you selected. Also checking out how good the model went on those selected rights. You can also change between all the distributions of the data, the feature you selected. You can also select just the rights with occurrence, that they are the yellow ones. And then you can explore just the rights with occurrence or just the regular rights. And you can check how well the model went on those rights too. So they evaluated it and they really liked the origin destination plot, because they were, as we talked before, they were really interested in understanding those rights that come and go from regions that are nearby. Because they noticed that there are some patterns, some people that call some rights from specific origins or destinations to commit some crime. So this, for them, was the most interesting feature of the tool, because it was really what was in their heads when we were really talking about this. So some conclusions here. We use some data science applied to a relevant safety issue, that are the safety of the drivers in these ride-hailing services that are usually not secure enough. We built a library to integrate data from different sources and formats. We also built a predictive model that takes imbalance into account and was very effective on that. We built a visualization tool to explore the data, considering several data sources, ordering of the coordinates, interactive selection of the rights, feature importance in prediction, and feature values exploration. As feature works, we would love to improve that ordering of the coordinates. I don't know how much better it can get. If you have any insights about it, please give us. That would be awesome. So predictive model based on the graph structure. We would like to apply some graph deep learning on the structure of the graph of the city. That's a really on-brand thing. Like, people are doing that a lot, and they're getting a lot of good results. We know that when we talk about graph, deep learning cannot be that deep, because otherwise you spread the information all over the place. So but it's an interesting take on the problem. And we also need to investigate some fairness aspects of the model and the visualization too, so we don't make any, or at least the least amount possible of injustice, lack of justice in the application. So these were the people involved in those projects. So gracias.
Victor, very nice. Thank you. I think that was interesting. I never seen that particular need of mapping this two-dimensional object to a one-dimensional one. So that was very nice for me. Thanks a lot.
Great. It's great that it gave you some insights too. Great to know.
Yeah, great. So I don't know if anybody else has a question. I think some people are already leaving because we are close to lunch, and it's
Yes,
usually we finish at 12:30.
So sorry
No.
about the delay. I didn't even notice.
No, no
I,
problem.
I really planned it to be a 30-40 minute presentation.
Right.
But
So we made too many questions.
I think it was part of me. I was part of the problem too.
No, it was great. So I think maybe we can write you in case we need. So it's very nice.
Feel free to write. Those are the emails. If you want to write any of us, we'll be happy to clear any doubt.
Okay, great. Thanks a lot. Say hi to Gustavo, please.
I'll do.
Okay. See you.
Thank you for your attention, people. Bye.
Very welcome. You can send also your friends if you want to present. We are, it's nice to see what other people are doing.
Great.
Okay.